This morning, I should say. This morning we are going to look at the properties of logarithms, some more things that we can do with logarithms. Remember, keep in mind at every moment, when you are finding a logarithm, you are finding an exponent. You've got to keep that in your mind. So, some things that we can do with logarithms. The product property says this. If I have the log with any base of two things that are being multiplied, the log with any base of two things that are being multiplied, if I want to break that apart, I can say the log of any base of the first thing plus the log of any base of the second thing. So, the log of a product is the sum of the logs. If I'm taking the log of two things that are multiplied, I can break them apart with addition. All right, now hopefully that means that it would make sense to us that if I have the log of two things that are being divided, I should be able to break them apart how? Subtraction, absolutely. That's going to be the log of the base of the first, subtract the log of the base of the second. And yes, order matters there. Order matters there. It has to be the log of the numerator, subtract the log of the denominator. Order matters. And then we have the power property. This is the one that I refer to as Superman. If I have the log, any base, of something to a power, if I have the log of any base of something to a power, that power is like Superman. He has the ability to fly out in front. So that's going to be n times the log of the base of m. The log of a power, the exponent has the ability to fly out in front. Okay, now how are we going to use these? One way, one example of a possibility to apply this is, let's say that we know that log base 3 of 12 is about 2.262. And we know that log base 3 of 2 is about 0.631 because we can see that 3 to the 2.262 does give me about 12. And 3 to the 0.631 does give me about 2. Now, these are the only two logs that I know. These are the only two logs that I know, and I know that my calculator is useless to me. My calculator is useless to me. Why? Yeah, my calculator only does two bases. It does base 10 and it does base E with ln. So my calculator isn't going to give me those. And that means that if I'm trying to find log base 3 of 6, my calculator isn't going to help me find those either. However, if I look at log base 3 of 6, they gave me log base 3 of 12 and they gave me log base 3 of 2. So if I use 12s and 2s, how do I build 6? 12 divided by 2, absolutely. So log base 3 of 6 should be log base 3 of 12 divided by 2, using 12s and 2s to make a 6. Now, if I have the log of two things that are being divided, Karina, what are you thinking we can do to break that apart?
The log base 3
of 12. Beautiful. The log of a fraction, the log of two things that are being divided, is the log of the first, subtract the log of the second. Well, I know that log base 3 of 12 is the 2.262. Subtract, I know that log base 3 of 2 is 0.631. So, all right, what is 2.262? Subtract 0.631. What do you get? Come on, calculators out. Rise and shine. Let's go, folks. 1.631. Now, do I have any idea if that's right?
No.
Can I check that?
Nope. We'll take a word for it.
I know that we're assuming log base 3 of 6 is equal to 1.631. How can I check that? All right, very quickly on your calculator, take 3 and raise it to the 1.631 power. And then watch the magic. What is it? About 6. Yep, better than Disney once again. All right. Now, log base 3 of 24. All right, I know 12s, I know 2. How do I get 24 from 12s and 2s? 12 times 2, absolutely. So that means that I know that this is log base 3 of 12 multiplied by 2. All right, Brooke, how am I going to break this apart?
Log base 3 of 12 plus log base 3 of 2.
Beautiful. All right, so we got log base 3 of 12 of 2.262, and we're going to add that to log base 3 of 2, which is 0.631. All right, what's 2.262 add 0.631, Levi? $2.893. All right, Miss Tiffany, how are we going to check that? Okay, so I have log base 3 of 24 now that I think is equal to 2.893. All right, I'm going to take 3 to that 2.893 power. What do you get? What do you get? Pretty close to 24. Isn't this beautiful? Yep, I know everybody's heads are shaking. Yes. All right, perfect. All right, so log base 3 of 32. All right, folks, how do I get 32 from 12s and or 2s? How do I get 32 from 12s and or 2s? 2 to the 5th. 32 is 2 to the 5th. So I have log base 3 of 2 to the 5th. Now, does anybody have a thought on what I can do here? That exponent of 5. Yes, he's Superman. He's putting on his glass, taking off his glasses. He's changing from Clark Kent into Superman. And he has the ability to fly out in front. So this is 5 multiplied by log base 3 of 2. When there's an exponent inside of the log, it has the ability to fly out in front. All right, now 5 multiplied by, well, log base 3 of 2 is 0.631. All right, Miss Jocelyn, what do you get for 5 multiplied by 631 thousandths? 3.155. All right, so I am making the assumption that log base 3 of 32 is equal to 3.155. All right, Brennan, what do I do to check? Yep, 3 raised to that exponent of 3.155, and what'd you get? 32.4. Pretty close to 32. Exciting. All right, one way to use these properties. All right, another way to use these properties is to do something called expanding our logarithm. Sometimes our logarithms become a whole lot more manageable if we can break them down into smaller pieces, if I can break them down into the smaller components. So if I have the log of 3x over 4, what is the first thing that you see inside of that log? What? Oh, yep, there is no 10 for the base. Absolutely, we are definitely in base of 10. Perfect. What else do we see? Dividing, absolutely. How do I break apart division? Subtraction. So I know that I'm going to have the log of my numerator, which is 3x, subtract the log of my denominator, which is 4. Okay, now the log of 3x. Miss Kendra, what's going on in between there? Multiplication. And how do I break apart multiplication? Addition. So that means that I have the log of 3, add the log of x, and then I'm subtracting the log of my single item 4. Now, once they're down to a single component, you can't break them down any further. So I realize that I am in log base 10. So is there 10 to a power that gives me 3? Is there 10 to a power that gives me x? No. What about 10 to a power that gives me 4? No. So this is expanded. This is as best as I can do. I broke it down into its smallest pieces, to its smallest components. Now, let's take that idea into B then. Taking that idea into B. Samantha B, what's the first thing you see when you look in there? Yep, I see a root also, and that looks kind of scary. What's going on with that root? It's getting multiplied by the 6 inside of that log. Absolutely. Now, how do I undo multiplication? Adding. Good. So that means I have the log of my first item, 6, added to the log of my second item, which is the 4th root of x. Okay, log of 6. What base am I in, Kaylee? 10. 10 to what power gives me 6? Nothing. Okay, that's not good. So I just have log of 6 plus the log of the 4th root of x. Now, remind me. Okay, the log of the 4th root. The 4th root is the same as what? X to the 1/4. That's the same as the 1/4 power, which makes this really interesting. So I have log of 6 plus what happens to that 1/4 power? It can fly out in front, absolutely. A power inside of a log, it's like Superman, it can fly out in front. The 1/4 of the log of x. So I have the log of a single thing, it's a variable, I know that I won't be able to do anything with that. All right, try C on your own. Very quickly, try C on your own. Yep, log base 7, and my fraction is 3x squared over 5y cubed. Keep in mind that everything we have been doing so far this morning will definitely be on a no calculator portion of your next quiz. Isn't nice. It's not, if this were 100, I would change it because it's nice. It's a tool. Does that make sense? Lots of steps in this one. Lots of steps in this one. All right, are we ready to give it a shot? All right, so here we go. What's the first thing we see? All right, division, so we know we're going to break it apart using what? Subtraction. Okay, so I have log base 7 of my numerator 3x squared, subtract my log base 7 of the denominator, which is 5y cubed. Now, I'm going to look at this first part all by itself. What is going on in between them? Multiplication. So how do I break them apart? Addition. So that's going to be log base 7 of my first item 3 plus log base 7 of my second item, which is x squared. Subtract All right, now I'm looking at this. What is going on in between them? Multiplication. So how do I break them apart? Addition. So I have log base 7 of my first item 5 plus log base 7 of my second item y cubed. But now I need to make sure that I understand this. I was subtracting all of this, which means that I need to be subtracting all of that. I was subtracting this log base 7 of 5y cubed, so I need to be subtracting both of those components that came from log base 7 of 5y cubed, which means I need to do what with that subtraction? Distribute. Okay, so I got log base 7 of 3 plus log base 7 of x squared, subtract log base 7 of 5, subtract log base 7 of y cubed. Okay, now I got some thinking to do here. Log base 7 of 3. 7 to what power is 3? Nothing. It's staying log base 7 of 3. Plus, what about this? The 2 is an exponent inside of a log. It can fly out in front. 2 log base 7 of x. Subtract. What about log base 7 of 5? 7 to what power is 5? So log base 7 of 5. Subtract. What about this? My exponent of 3 can fly out in front. So 3 log base 7 of y. Any questions on that one? Any questions on that one? All right. Flip over to the next page. Keep on working. Now we're going to work on condensing. Okay? Condensing means that I'm going to put it back together. Condensing means that I'm going to put these back together. So, take a look at A. Is there anything that I can put together? Is there anything, raise your hand, that I can put back together? Yes, ma'am. All right. Log base 3 of 5, add log base 3 of 15. If my two logs are being added, how do I put them together? Multiplication. So I have a single log base 3 of 5 multiplied by 15. So 5 times 15 is 75 plus log base 3 of y. Connor G, what are you thinking now? Beautiful. I have two logs that are being added. So to put them together, that means I have a single log of their product, 75 times y. Notice, these two logs go together to be one log. Notice that these two logs go together to be one log. Putting them together, two logs to make one log. All right. Somebody have a thought in B? Somebody have a thought on something that we can do in B? Beautiful. The 2 out in front has to fly up to be the exponent inside. So we have the log of 6 squared minus the log of m. What's 6 squared? 36. We have the log of 36. Subtract the log of m. Katie, are you thinking anything else we could do? Beautiful. It's subtraction, so I can divide. So that's the log of my first item. 36 becomes the numerator. Divided by my second item, the m becomes my denominator. All right, try C very quickly on your own. All right, Brennan, what's the first thing you're going to do?
Bring it to times the square root of 5.
Beautiful. That 2 out in the front becomes an exponent inside, so you have the ln of 8 plus the ln of 5 squared minus the ln of 10. And 5 squared is what?
25.
Beautiful. So 5 squared is 25 minus the ln of 10. All right. Ms. Tessa, what's the next thing we do?
since ln 8 and ln 25 are adding, I multiply them.
Beautiful. Because these two are being added, I can multiply them. So the ln of my first item, 8 times 25. So 8 times 25 is 200. Beautiful. All right, Daria, where do we go from there?
200 divided by 10.
Beautiful. If my two logs are being subtracted, I can divide. So that's the ln of my first item, 200, divided by my second item, 10. So it becomes the ln of what, folks? 20. All right. Now, we have already discussed the fact that my calculator can only handle what kind of logs? Base 10 and e. Base 10 and base e, natural log, the common log and the natural log. But we have the ability to change the bases of our logarithms. Okay? Here's the deal. Log base c, log with any base of a number, means that I can change it to the log of any base of the a value divided by the log with any base of the base from before. Now, two most common ones are going to be to change it to log base 10 and ln because they're the nicest for us. So for example, if I had log base c of a, I might want to take the log of a divided by the log of c in my calculator. Or if I had log base c of a, I might want to take the ln of a and divide it by the ln of my base, which is the c. We have the ability to change the base to any base we want. However, base 10 and base e are going to be the most useful, the most helpful because of our ability to use our calculator to find those exponents. So, if we look at log base 6 of 24, in other words, 6 to what power is 24? Is 6 to an exponent equal to 24? 6 to what power is 24? It's not nice. But I have the ability to let my calculator help me. If I simply take the log of 24 and divide it by the log of the base, 6. I am in what base now? What base have I changed it to? 10. I've changed them both to base 10. The log of 24 divided by the log of 6. Very quickly, take the log of 24 and divide by the log of 6. 1.77, and I think it's even 37. Now, remember, I can check. Log base 6 of 24 should be approximately equal to the 1.7737. How do I check that, Alex V?
You just do 6 to the 1.7.
All right, very quickly, take 6 to the 1.7737. What do you get? Yep, pretty darn close to 24. Now, I didn't have to change it to log base 10. I did not have to change it to log base 10. I could have done log base 6 of 24, and I could have changed it to the base of e. I could have changed it to base 3 or base 5 or base 9, but they're not going to help me like base 10 or base e, the ln. So, let's try it out here. Log base 6 of 24. Well, if I take the ln of 24 and divide it by the ln of 6. Very quickly, take the ln of 24 and divide it by the ln of 6. What do you get? Yeah, 1.7737. Is that shocking? No, because 6 to the 1.7737 is about 24. It has to be the same no matter what. All right, one last application situation of these logarithms. And this is a very interesting application because this is exactly where this comes from. Richter scale for earthquakes is something that a lot of people do not completely clearly understand. The Richter scale is used to measure the magnitude of earthquakes. If an earthquake has an intensity of I, then its magnitude on the Richter scale is given by a function R of I is equal to the log of I over I sub 0. I sub 0 is the intensity of an earthquake you hardly even feel. If the intensity of an earthquake is 50 times that of another, how many points greater is the bigger earthquake on the Richter scale? Okay, now, if I want to know how much bigger something is than something else, what am I doing? What math operation? I have one building and I want to know how much bigger it is than the other building. What am I going to do? Subtract their heights, right? If I want to know how much bigger something is than something else, that means I'm going to be subtracting. So, let's keep that in mind. That means that I want the Richter scale value of the larger earthquake, subtract the Richter scale value of the small earthquake, to see what the difference is. Okay, now what do we know about the large earthquake? It's 50 times greater. Okay, so if this small earthquake is R of I, if this small earthquake is R of I, that means that I know the large earthquake is going to be R of 50I. It's going to be 50 times bigger than the small one. Is everybody okay with that? Is everybody with me on that? Question so far? Okay, now, they've already told me that R of I is the log of I over I sub 0. R of I is the log of I over I sub 0, being subtracted from, well, R of 50I. Now, hopefully we realize then, if I have 50I, that's the log of 50I over I sub 0. Is everybody okay with that? Is everybody okay with that? Any questions so far? All right, now, can I subtract these right now? What is that? Are they common? Are they like terms? No, so I can't be subtracting them. What can I do? Does anybody have a thought? Anybody have a thought? Let's expand them. Let's break them apart into their smaller components. Okay, so the log of 50I over I sub 0. All right, Leslie, what's the first thing I'm going to do to expand that quantity? Beautiful. The log of two things that are divided is the log of their difference. So the log of the numerator subtract the log of the denominator. Subtract. All right, how's that going to look over here, Connor G?
Log of I minus log of I 0.
All right, now remember I'm subtracting this entire quantity. So that means I need to distribute. So I have the log of 50I, subtract the log of I sub 0, subtract the log of I, subtract a negative, so that's going to be plus the log of I sub 0. All right, any comments? Log of I sub 0 here, negative log of I sub 0 there, they're going to cancel right away. Okay, so now I have the log of 50I, subtract the log of I. Beautiful. Anybody got any more thoughts on where we should go? Comments? All right, what can I do with that log of 50I? Break them apart. And how am I going to break them apart? What's going on in between them? Multiplied. So how do I break them apart? Add them. Good. The log of the 50, add the log of the I, subtract the log of I. All right, Katie, what are you thinking?
The logs of I.
Yep, positive log of I, negative log of I cancel, and what do we get? Log of 50. Now, please explain to me what this is saying. What base am I in? 10. And when I'm finding a logarithm, I'm finding an exponent. So I'm asking 10 to what power gives me 50, right? 10 to what power gives me 50? Very quickly, take the log of 50. What is it?
1.69897.
Okay, fair enough to say about 1.7? Okay, now keep in mind that that means 10 to the 1.7 is equal to 50. That means if tomorrow we have an earthquake that's 6.0, and the next day we have an earthquake that is 7.7, how much is the bigger one? How much worse is the bigger one than the one that is smaller? 50 times worse. 1.7 difference on the Richter scale means that the earthquake is 50 times worse. Sometimes people think, oh, if it's a 7.1 and then a 7.2, that's pretty much the same. That's not true. It is a logarithmic scale, and we should understand that because when you're finding a logarithm, you're finding the exponent, which makes the intensity much greater. Because it's a logarithmic scale, because you're finding the exponent. Exponents make that intensity much greater. A smaller change means a much greater change in intensity. Does that make sense? Do you understand the effect of having a logarithmic scale? Even though there's only a 1.7 difference in the values on that scale, it is 50 times worse. And that is based because it is a logarithmic scale, because you are finding that exponent. Questions? Okay.